Okay, so let's start. So last time we talked about series and we introduced several methods of testing the convergence and divergence of series. So the easiest way is the nth term test, the first one right here. This is the easiest one. And there's no condition on each series, each term in the series. And the next thing, if the nth term test fails, which means that if the limit of sequence goes to 0, then the next thing you have to check is the ratio test. And there are also no condition on each sequence. And what you have to check is the limit of the absolute value of the ratio. And if that limit of ratio goes to it's always positive number, but it goes to number bigger than 1, then it's diverging. Less than 1, it's converging. Equals to 1, then we don't know from this test whether the series converge or not. And the next thing you have to check is the root test, but these two tests it has a different nature, so you have to choose between these ratio test or root test to which one you will use. So if it's easy to check the ratio, and then you have to use the ratio test. If it's easy to check the nth root of the sequence, then you have to use the root test. And the next thing is that the geometric series test. This is not a test you can use independently, because usually this is the well-known result. So basically, you know this from high school, that you have a geometric series, then the condition that this series converge is that this x, the ratio between consecutive sequence, has an absolute value less than 1. And if it's bigger than or equal to 1, then it's always diverging. And the next thing is the power series test. So this is not a geometric series. It looks like this. So 1 over p n to the p. So n from 1 to infinity. So p can be either natural number or any real number, positive real number. So if p is bigger than 1, then it always converge. If p is less than 1, it always diverge or equal to 1. So to prove that this, so this is not really a test, but this is almost like a fact that this kind of series always converge or diverge depending on the condition on p. So if you want to prove this, you can use the integral test on this page. So it basically says that if you have a series whose sequence is decreasing, not necessarily monotonic, but it's decreasing, and if you can choose a function whose value at the integer is equal to the sequence, and the condition is that if the improper integral of this function f from some natural number to the infinity converges, then the series converge. If it diverges, if this improper integral diverges, then it diverges. So look at the condition on this series. So we assume that the sequence is always positive, so this function must be always a positive function, okay? So whenever you take the improper integral, it's either diverges to positive infinity or converges to finite number. So let's look at the power series test again. So we have an as 1 over n to the p. So let's define my f of x as 1 over x to the p. In that case, f of n is equals to an, right? So I draw this picture last time briefly, but let me explain this again. So whenever I take a series, let's try to put a dot on this two-dimensional plane. Let's say this is x, but when x is 1, 2, 3, 4, and so on, let's try to put A1 and A2 and A3 here. So A1 right here, and A2, A3, and so on, A4. So if you're looking at the area of a rectangle, each area is actually the value of AN, right? So this is A1, this is A2, and A3, and A4. So the series AN is the sum of all, so infinitely many, areas of rectangles. Okay? So and then let's look at the improper integral. So improper integral is the area of a function which connects these dots here. Okay? And to see whether the area of a rectangle is finite, the sum of area of a rectangles are finite, it's equal to show that the area under the graph of the function y equals to f of x is finite if I take the domain of integration to from finite number to infinity. So it doesn't matter some finite, the first finite few terms is negative or positive or some other value because it's always finite. What matters is the tail of the series. So let's pick some large number because I don't care about the first few terms. The first few terms may not follow the value of function. What matters is the rest of the term will always follow the function. So it is okay for the first few terms of AN not following the identity as long as f of m equals to am for m bigger than from some large n. So let's cut here and let's compare the area under the graph, which is n to the infinity of f of x dx. And the sum of so here you have n plus 1. So I choose 2. So it's going to be adding the sequence from n plus 1, an. So you see that if I take the rectangular area like this one, then the area under the curve is always bigger than the sum of rectangles. So we have this inequality. Now, it means that if this diverges, if this improper integral diverges, then this diverges. Okay? If this diverges, then this diverges. Okay? How about opposite? How about in the opposite situation? What if this converge? Then, okay, so, I'm sorry, so I made a mistake here, so sorry. So this is bigger, sorry. So this is converge, sorry. If this part, the larger area converges, then this smaller one must also converge. Okay? So there's a delay, so probably ask this in the chat, but okay, so I made a mistake. So the area under the curve is larger one, so if your larger one converge, then smaller one also converge. So what if the situation is opposite? What if this larger area, the area under the curve, diverges? because it's an improper integral, it could diverge, then we cannot say anything about this sum of areas by looking at this inequality. However, if I take the area of a rectangle in a different way, then I can make a different, the opposite inequality. So let's take height of a rectangle from the left-hand side. So in the right, this yellow rectangle, I choose the height of the rectangle from the right-hand side. But let's choose the height of the rectangle from the left-hand side. So this blue area is now become A1, A2, and A3, and so on. So in that case, this improper integral from n to infinity of f of x dx is now smaller than the sum of n equals to large N. So I choose this to be n equals to large N cut line and to the infinity an. Okay, so if this now diverges, then this also diverges, because the smaller diverge, then the larger diverge, obviously. So what it says is, so what we compare with the improper integral is not exactly the same tail, but we have a one term difference between these two tails. But as I mentioned, it doesn't matter if I include the nth sequence or not, and not in here. So we have no nth sequence in the series here, but there's an nth sequence. So it's just the an difference between these two infinite series. It doesn't matter to check whether these converge or diverge. So basically, the convergence and divergence of this improper integral and the tail of the series are the same. So we can just simply look at this improper integral to check whether the sequence is converged or not. So let's look at the improper integral of fx, 1 over xp dx. So this is defined to be, when b goes to infinity, it's n to be of 1 over xp dx, and limit of b goes to infinity of minus, here we have so it was x to the minus p, so minus p plus 1 over x to the minus p plus 1, right? Minus p, yes. Okay, so and then we have nb, so minus, so just 1 over minus p plus 1 of bp minus 1 and np minus 1. Okay, so now we have a situation when p is less than 1 or equals to 1. Okay, what happens? So n equals to 1 is a little bit different situation. We didn't include that case here because I assumed that p is not equals to 1 to say that the antiderivative of this 1 over p squared is this one. So let's compare, let's consider p equals 1 case separately. So whenever we have p less than 1, now this is a negative on the power. So it becomes the b to the 1 minus p, which is 1 minus p is positive power. So when b goes to infinity, it goes diverge. So we have a infinite. When p is positive, so when p is bigger than 1, then this one has a positive exponent in the denominator. So when b goes to infinity, this denominator goes to infinity. Therefore, 1 over infinity is 0. So this is a finite number, so it goes to finite number. So it converges. So actual value of convergence is not important because by this inequality, we are not trying to find exact number of this limit. We only compare the two tails of the series and then check the sequence, check the convergence and divergence of the series. So what happens when p equals to 1? So when p equals to 1, so this is when p is not equals to 1. If p equals to 1, then we have antiderivative of ln x from n to b, and this is similar situation when p is less than 1. When b goes to infinity, ln b goes to infinity, so this diverges. So this proves the nth term p-test. Okay, so also let's mention this alternating series test, that each sequence is minus 1 to the power of n times bn, where bn is always positive, so the sign changes. And another condition is that this absolute values term bn is decreasing sequence. So if the absolute value of the series sequence goes to 0 when n goes to infinity, then this alternating series converges. So here's an example. So if you're looking at the last one, so log of 1 plus 1 over n. So this is an alternating series test because we have an alternating sign. And let's compare, or let's try to look at the limit of this absolute value here, absolute value part. Okay, so this is equals to what? Limit of, so a log is continuous function, so I can put this limit inside of log. So this is basically the, I don't have to write the limit here. So log of 1, so this is 0, okay? So it goes to 0, okay? So you shouldn't confuse with alternating test with nth term test. So nth term test says that if the limit of sequence goes to non-zero value, then it diverges. This series has a sequence whose limit is equals to 0, right? However, the reason why we can conclude that this converge is because it's alternating series. The sign changes. So idea behind the convergence of alternating series is the following. So you have an alternating series as a point on a two-dimensional plane. Then let's try to plot the partial sums here. So we have A1, which is S1 at n equals to 1. So instead of drawing the points of sequence, I'm trying to put the points on the series. So every point is n comma Sn, where Sn is A1 to An sum. Okay. So now A1 is positive, obviously, so I choose A2 to be negative value, but absolute value of A2 is less than A1 because of the assumption. So when I put S2 here, then it's decreased by absolute value of A2, but it's not become negative because A2, absolute value of A2 is less than A1, so it doesn't go to the negative side. Okay, so we have moved to S2 here. So the difference, this difference is now A2. Okay, so that's for more rigorous, it's a negative absolute value of A2. So this is now this is A1 minus A2. Okay. So and then let's add A3. Okay, so A3 is now a positive number whose absolute value is also less than A2. So when I add A3 to S2 to get S3, I'm not going above this A1. Okay, so this is A2. A3 is the length of A3 is smaller than length of A2. So I can move under the A1 here. So this is A3 and this is S3. Okay, and you do this for entire n. So you keep doing this. The next time you add A4, you're not going below this S2, right? Because A4 is less than A3. So and so on. So you get this up and down sequence, but eventually it will converge to some number in between this A1 and S1 and S2. Okay. So this is the idea behind why alternating series always converge, provided the sequence has this property. So let's look at the first one. So we didn't mention the comparison test. However, the full use of comparison test is very hard. It's almost state of art to show whether series is converged or not using the comparison test. So in this case, there are many ways to prove this type of this series is convergent. One way is comparison test, but you can also use the limit comparison test. So how to use the comparison test? In order to use the comparison test, you have to assume you have to have a least idea whether this series converge or diverge. Because if you're looking at the comparison test here, it depends on what you have to show to choose your comparing sequence. So if you want to show the given series is convergent, then you have to set your comparing sequence Bn as a larger sequence than the original sequence, and then also this larger sequence has a convergent series. Okay, so if you want to show that the original series is divergent, then you have to choose a smaller sequence and the sum of sequence diverges. Okay, so the idea is simple. If the smaller one diverges, then the bigger one diverges, and a bigger one converges, then the smaller one converges. But choosing such Bn carefully is a hard issue. So we have following sequence, and I know by my experience that this is convergent, because one way I can check whether this is convergent is that this is almost equals to 3m squared minus 102. Because if n is quite large, the 100, if you think the 100 is large, but n could be 100 to the power of 100, and it's almost 100 itself is almost nothing. Okay, so this is almost equals to ignoring minus 100 in the denominator. So this one is nothing but 2 over 3 times 1 over n squared. So this has 1 over n to the p form, and where p equals 2. So by the p-test, when p is bigger than 1, we know that this converges. So we know that this is convergent, but this is just an idea. This is just a guess. So I have to use my comparison test to by setting my Bn carefully. So my Bn should be so if I take this as an, Bn should be a sequence bigger than an, and also the series converges. So what kind of Bn can I use? So easiest one is that if I make a suppose that I make if I want to make a ratio bigger, then I have to make the denominator smaller, right? I have to make a smaller denominator. However, if I just simply remove minus 100 and choose 3n squared to the 2, then this is not the right bn satisfying this inequality because denominator got bigger. So actually bn is less than an. Okay, so I cannot choose this bn as this 2 over 3n squared. So what kind of bn can you use? This situation. So we have a few second delay. So idea is you want to make your denominator smaller, right? Make it smaller. So if you use bn as 2 over 3n squared, that's a good question, then does this inequality hold? So bn has a larger denominator, right? Larger denominator means you have a smaller ratio. So bn is actually less than an if you use this as a bn. Okay, I want bn as a larger value than an, so that if the bn series converge, then an series converge. So what other options that you have? What kind of bn you want to use? Just make it smaller. How do you make it smaller? 지금 6명밖에 안 들어오 있는 거 뭐야? 지금 진짜 6명밖에 안 들어와 있는 거예요? 보고 있는 사람이 12명이고 채창에 6명밖에 없다고? 나까지 합해서 6명인데? I'm not gonna tell you the answer because there's so many so small people listening this lecture right now, so I don't have to write. I don't have to tell you the answer for those who does not take the course on time. So I'm going to so I'm going to write it in a LMS chat instead. So no, it's okay to take the YouTube, but the viewer in the YouTube is only 13 people right now. Okay, so we have a 53 students enrolled this class. Okay, also take the midterm, and now only 13, including me, actually 12 people listening this lecture on time. So the answer is it's on the chat. Okay. Does that make sense? Because does it make sense? Okay, so this is our secret. So don't tell anyone who doesn't take the course, who doesn't listen to this lecture on time. Okay. Not others. Okay, that's it. So you can solve the first one either by using the comparison test and sorry. So let me also write that in the chat. So the first convergence, first series can be okay. So there are two ways of checking the convergence and divergence of the first series. Okay, that's important. Okay, so let's move on. The power series. So series of this form, so we have an x, so we have an undetermined variable x inside of the series. And this type of series, and also we have a power on each term with some coefficient an, is called a power series. So it's basically a series if you fix x. However, usually we don't fix x and we plug in numbers to x and then see what the limit of this series are. You could have a diverging sequence if your x is large or small. But anyway, this is the former series, so-called, and we call it power series. So important is the radius of convergence. So radius of convergence called r is the length of the x from the center where this power series converge. In other words, so if x equals to c, so in this form, then x minus c is always 0. So 0 power n is always 0. So everything goes to 0, okay? Except for a0, sorry. Now, so if x equals to c, then this power series always, sorry. Okay, so power series always converge. So I want to find out how far I can move my x from the center C, so C is called the center, so that the power series still converge. So that's a radius, okay? And the interesting thing about the radius is always symmetric. So if you move your x from the center C to the epsilon to the right, and then the series still converge, then the series also converge when you move your x from the center C to the left by epsilon. Okay, it's always symmetric. Okay, so this is a description of, so whenever R is a finite number, not zero or not infinity, then we say that power series, we define our R to be the value where the power series converge for every x satisfying this inequality. So basically, if you have the real line real line for x, and then there's a c, and then you have c minus r here and c plus r here. If the power series converges for all the points inside of this open interval, so does not including the boundary here, then if you take the x outside of this open boundary, strictly outside of this this open boundary here, we have x here, then it diverges. So if it diverges and converges here, then r is the radius. Okay. So what happens to the boundary? Okay. So at the boundary, the series could converge or it could diverge. We don't know. We have to check it directly by looking at the series. However, we also define R to be 0 or infinity. In a special circumstance, when R is 0, it means that the power series only converges at x equals to c. Whenever x deviate from c, the center, slightly, then the series diverges immediately. And if R is infinity, that means I can plug any number to x and the series is still converge. Okay. Okay, so here's an example. Let's look at the example first. Okay. I explained this theorem already. So we have a power series whose center is all 0. The c is always all 0 in the power series. So let's look at the first one. So we have x to the n factorial, n from 1 to infinity. Okay. And suppose that we have a fixed x, and suppose that we n factorial, not n factorial, just n, sorry. Suppose that we have a given fixed x and try to find out convergence and divergence of this series. Okay, so whenever you choose, you test this kind of series, let's try to use the ratio test, okay? Because we have powers here. If you take the ratio, then the power cancels out and the ratio becomes simple. So ratio test says that if I take the limit of, so this is now considered to be an in the ratio test. So an plus 1, an absolute value is now become x to the n plus 1, x to the n, okay? And this is equals to n plus 1 n times x when n goes to infinity. So when n goes to infinity, it goes to 1. So this is because simply absolute value of x. So now let's think in the reverse way. So although we assume that x is a fixed constant, if this x were a value whose absolute value is less than 1, then by the ratio test, this series converge. Okay. So if x were satisfying this condition, then x to the n, this converge. Now, in a different situation, if this were bigger than 1, strictly bigger than 1, by the ratio test, this series diverges, right? Therefore, if the absolute value x is bigger than 1, then this diverges. So it says we have a center. This is the center of power series. Okay? And if x lies in between 0 from -1 to 1, then this converges on here. And it diverges outside on the left. Okay? So therefore, I cannot pass this boundary. I cannot pass the radius 1. So radius is 1. Okay? So therefore, radius equals to 1. So here's one more question. There's a definition in the next slide. So we have a radius of a convergence. Now, what's the interval of convergence? So the interval of is the interval of x where the power series converges. Okay. So in this case, we only know we only know the radius. So interval of convergence could be -1, 1, or -1, 1 closed on the right, or -1, 1 closed on the left, or closed on both sides. Which one is the interval of convergence? It only matters to check the convergence and divergence on the left end and right end. So let's try to plug in x equals to -1 there. So we have sum of -1 to the power of n over n from n equals to 1 to infinity. Now, this is an alternating series. Therefore, if the absolute value part of this alternating sequence converges to 0, this series converge. So absolute value part is 1 over n. It goes obviously to 0 when n goes to infinity. So this is converge by alternating series test. Okay. So -1 is included in the interval of convergence because it converges. What if I take x as a right end, which is 1, then the series becomes 1 over n from n equals to 1 to infinity. So this is a p-test. So this is a form of 1 over n to the power of p, and p equals to 1. So p is 1. By p-test, it diverges. Okay. So in the interval of convergence, it includes -1 but not 1. So the interval of conv is -1, including -1, but not including 1. So there's a difference between computing the radius of convergence and interval of convergence. Okay. And you can check whether the rest of the computation. But okay, so here's the interesting part. So we have 2 more series. Okay. I'll show you the answer, and you can try yourself why that answer is true. So we have n factorial x to the n has radius infinity, and n factorial x to the n has radius 0. So this means this power series converges whatever value of x is. Okay. So in this one, it does not converge except for x equals to 0. So if x has a non-zero value, then this always diverge. You can prove this using the same ratio test. Let's keep moving. We have a few more time. So here's a theorem. It's not really a theorem. It says that if you want to find your radius of convergence easily, then you can try to find out this ratio or this ratio. So this AN is not AN in the ratio test. This AN is the AN on the coefficient of power series. This AN, okay? So I usually don't recommend to use this theorem because it kind of confused with the ratio test because of the use of AN here. But let's look at the example here. Not using the theorem. If you are comfortable just not confusing with this the ratio test, then you can use it. But let's look at the examples without using this theorem. Oh, sorry, so I made it smaller pictures here. So this theorem, so this one is follow from the ratio test and the nth root test of the power series, but you shouldn't confuse this AN with the AN in the ratio test or nth root test, because this AN is the coefficient in here. So this is a coefficient in the power series, okay? Don't confuse with that. So I don't use usually this theorem. So let's prove the three. Let's try to find the radius convergence and interval of convergence of these three power series. So the first one. So the type of power series in the first equation, first series, looks like I can use the nth term test. So nth root test in each sequence. So let's try here. So n equals to 1 to infinity, n plus 1 to the power of n x n. Okay. Let's try to take entire thing as an. Okay. And I'm trying to use the root test on an. Okay, so an including this x, or maybe I just take a same notation I used in the definition. So let's try to put this as a an times xn. Okay, so root test on an times xn. So this entire thing is an, okay? So how do you use the root test? You take the nth root of the series, an. So whenever you take the root test, the condition is that your sequence must be positive number. Here, this is positive number, but this x could be a negative number if you have a negative x inside. However, I can take x as a positive number at first by fixing x as a positive number, and then by the characteristic of the power series, if it's convergent on the positive side of the center, then it also converges to the negative side of the center. So I can safely assume that this x is positive for now. So the limit is n goes to infinity. So an is now nth root of n plus 1 to the power of n x n, and this is limit of n goes to infinity of an plus 1 times x. What's the limit? It's infinity. It cannot be a finite number because whatever I choose, so except for x equals to 0. So that's obvious because x equals to 0 is the center. It's always converge. So whenever we have x not equals to 0, then it's always infinity. So it means it never converge. This root test says that this series never converge whenever x is not equals to 0. So this series only converges at center. So the radius is equals to 0. Okay? So if the radius is 0, there's no no interval. The actual interval is the 1-point set. Let's look at the second one. So we have 2 to the power of n factorial x to the power of n when n goes to 1 to infinity. Now, in this case, it's easier to use the ratio test because the root test results nth root of n factorial, which is impossible to compute. So therefore, we use the entire thing as an times xn equals to an, and use the ratio test. So ratio test. So limit of an plus 1 an. Here we have 2n plus 1 n plus 1 factorial x to the n plus 1 2n n factorial x to the n. And here we have 2 n plus 1 2 absolute value x. Okay. What's the limit? It's 0. So it's always less than 1, which means that this series always converge. So no matter what value of x is, it always converges, which means that the radius is infinity. Okay. Now, if at this point, if you go back to the Cauchy-Hadamard theorem, look at the ratio here. So we have tried to put the ratio, the root test on entire sequence here, but you can split this limit as the nth root of x to the power of n and nth root of an, right? So what results is this one, okay? So this one. So this one is the result of this one, okay? Now, so if this has a some kind of a limit L, okay, and the root test says if L times x is less than 1, then it converges. If it's bigger than 1, then it diverges. So this implies that if x is less than 1 over L, then it converges. And if x is larger than 1 over L, it diverges. Okay? So what is 1 over L? So 1 over L is 1 over limit of this nth root of an. So in other words, you can take this as a limit of 1 over nth root of an. Okay? So that's 1 over L. And what's the 1 over L in this inequality says? It's basically the same definition for the radius of convergence. This is the R. Okay? If x, so we have a center equals to 0, that's why I have x. Instead, if I have a center C, then x minus C must be on the left-hand side. However, this is less than R, then it converges, and bigger than R, it diverges. That's exactly the same definition for the radius of convergence. So this is the R. Okay? And you see the definition theorem for Cauchy-Hadamard to find the radius of convergence looking at the ratio 1 over nth root of an. That's how we get how it derived from the root test here. So basically, you can simply apply the root test directly to the sequence power series, or you can use the Cauchy-Hadamard theorem. It's up to you. So it's same for when you use the ratio test. So this part, this part. Now this is equals to an plus 1 an times x. So this part is this one. Okay. So also if you move your limit to the right hand side, the radius is the limit of the reciprocal of this ratio. So an over an plus 1. Okay. Okay, so how the third one? The third one looks like alternating series. So you cannot apply the Cauchy-Hadamard theorem. Cauchy-Hadamard theorem only applies when an is positive. So when you have an alternating series, you have to use the definition of radius of convergence. N x plus 1 to the power of n. So now c is minus 1. Okay. So you have to remember that always you have an times x minus c to the n as a basic form of power series, and in order to get plus 1 here, you have to have c equals to negative 1. So negative 1 is the center. When x is negative 1, this always goes to n from 1 to infinity, so minus 1. Okay. I'm sorry, so n equals to 1, so it always goes to 0, sorry. Anyway, so try to use alternating series test. Okay. So you have a positive part of this alternating series, the limit of x plus 1 to the power of n over n. Alternating series test says if this goes to 0, then it converges. If this is 0, then it converges. What if it does not go to 0? It diverges, but not because of alternating series test, but because of nth term test. So nth term test says that the sequence goes to limit not equals to 0, then it diverges. So we have a convergence and divergence condition here. So whenever you have this ratio, so n goes to infinity, what goes, so when does it goes to 0 and when does not goes to 0? So n goes to infinity also. If x plus 1 is less than 1, so it's a number less than 1, then its power goes to 0, right? So suppose that x plus 1 is some kind of 1 over 1 plus c or something like that, okay? Maybe not c, maybe some alpha, okay? So it's because less than 1, okay? For example, it could be negative, but I'm just assuming, for example, take an example here. So what happens? The limit of x1 plus 1 to the power of n is now become the limit of 1 over n, 1 plus alpha, n here. And what happens? Or you can, yeah, well, you can use this. Like, so what happens here? What's the limit? 0. So this is like exponential. Exponentially goes to 0, and this goes to polynomially infinity. Exponential always dominates. Okay, so it's always 0. So what if you have x plus 1 bigger than 1? Then you have exponentially growing infinity, polynomially growing infinity. Exponential always dominates, so it goes to infinity, right? So it only matters of the absolute value of x plus 1. So whenever it's bigger than 1, it diverges. So let's draw the line here. So we have minus 1 and so here is 2 and here is sorry, so here is 1. Minus 1, 0 here, minus 2, and x plus 1, 2. Here, okay, so this is the radius. So we know that the radius of convergence is 1, so therefore we can move my x from minus 2 to 0 so that the series converge. This is the radius converge, and this is diverge here, diverge. So now when you have to check the interval of convergence, you have to check the convergence at the endpoints. When x is negative 2, we have minus 1 n times, when x minus 2 is minus 1 to the power of n. So we have 2 minus 1 to the power of n, which is always positive. So we have 1 over n. It always diverge. Okay. When x equals to 0, then this is minus 1 to the power of n over n. And we know that this converge because of the alternating series test. So this converge. So the interval of convergence includes 0 only. Okay. Okay. So this few positive x plus, so the question is x plus 1 to the power of n over n is positive. It's an infinity, sorry. So I'm not sure whether what part you're asking, but okay, so when you try to use the alternating series test, you have to use this part, a positive part, right? So that's true, but when you try to find the interval of convergence of a power series, because of the nature of the power series, if you know that your point x on the right is a convergent point, then the symmetric part, so here we have c plus epsilon, then we have minus epsilon plus c. This is also convergent. If this is convergent, then this is also convergent. So to check the radius, you can assume that this x is a number which makes this part positive number. Okay. Does it make sense? So it's like it's a little bit of it's a little bit of the cheating. So we're using a deep theory on the analysis. So, but our purpose is finding a radius convergence. But then it's okay to cheat a little bit. Okay, so we have a interesting arithmetic here. So we have suppose that we have a 2 power series. We can multiply 2 power series and make it as a new power series, or subtract. So divide 2 power series to make a new power series. So it's easy computation. It's like the multiplying 2 polynomials. So whenever you write your power series, you have to write from the lower power to the higher power. So when you multiplying these 2 power series, then try to find the lowest term created by multiplying these two power series. So you have a zeroth degree and first degree. So when you're multiplying these two, the lowest term must be the first degree, okay, degree 1. So that's obtained by multiplying x and 1. So there's x here. If you're multiplying any other term, then the degree is bigger than 1. So this is only degree 1 term. So how about degree 2? So only way you can obtain degree 2 by multiplying these two is either you take x and some degree 1 polynomial here, or x2 and degree 0 here, but there's nothing. Okay, so there's no degree 2 terms here. And degree 3 is obtained by multiplying these two, and these two. So this is the result of minus 1 over 6 minus 1 over 2. Okay, and so on. So this is usually you cannot find a general formula for the coefficient of product of series. You can only find the first few terms by brute force of multiplying two polynomials and try to find first few terms of the power series, product of power series. And same thing for the division here. So we are dividing a by bx. So let me do that in the board. I think you already done that when you're dividing the two polynomials. It's almost like a polynomial, so it's not hard. So we have x minus 2, so this is x minus 1 over 6 x cubed plus 120 x fifths and so on. And b is 1 minus 1 over 2 x squared plus 1 over 24 x4. So try to make your lowest degree term on B match with the lowest degree term on the A. Okay, so I have to multiply x, and the coefficients are luckily to be equal 1, so I can just take x and multiply x on the series B. So there are infinitely many terms here, but I just did not write it. So we have x minus 1 over 2 x cubed and 1 over 24 x fifths. And then subtract that. So we have 1 over 2 minus 1 over 6 x cubed and 1 over 120 minus 1 over 24 x fifths. So and then make this the lowest degree term of B and this division, what's called a remainder the same. So we have 3 over, is it right? 6 over 3. So yeah, 3 over 1 x cubed multiply on B, so that I get 1 over 3 x cubed and minus 1 over 6 x fifths and 1 over 72 x sevenths and so on. And you subtract again. So this will cancel out, and then the rest of the term will be some coefficient times x to the power fifths and so on. And you do the same thing. You keep doing this until you're satisfied. Okay. I'm not saying that you can do this for infinitely many times, because you have to do this computation for long times. As long as you have a complete formula of a complete some reciprocal formula, then you can find the general form of this coefficient. 잘 안 보이는데. 좀 그렇네요, 지금. 지금 좀 그런데, 제가 고정 초점하는 기능을 잘 몰라가지고 자동 초점인데 좀 공부를 더 해서 나중에 고칠게요. Okay. Okay, so that's it. And then everything we learned so far, it's important to understand the series solution of the differential equation. So the main point, so the most important ingredient on the series solution is the Taylor series. So it basically says if you have a function which is infinitely many differentiable. So C infinite means that it's infinitely differentiable. Okay? So you can take a differential for many times, infinitely many times. Then you can write your power series with this special coefficient. So when n equals to 0, 0 factorial is 1. So we have fc, the value of function itself. And the rest of the terms are the following. So you have f prime c, and the next term is f double prime c over 2 factorial times x minus c squared, and so on. So this power series always converge at the center c, which is the value of function at c. And then as every time you adding power terms, this series become more and more likely to the graph of function. Okay. Here's a example. So you have 1 over x, 1 minus x. You know that this is the limit of geometric series, and geometric series of the ratio x. So this converges only when x, absolute value of x is less than 1. So I put the equal sign here. Okay, I put the equal sign, but the previous definition does not say anything about equality of the function f of x and this series. This is not always equal, but I'm giving an example where the function are actually equal to the Taylor series at the interval of convergence. Okay. So when I choose the left-hand side function as original function and then try to find the Taylor series in the previous definition, then it's on the right-hand side here. Okay. So if I choose e to the x at the center c equals to 0, so this is center c equals to 0, and then when I take the Taylor series of exponential function at the center c equals to 0, then this is the Taylor series. And equality will be explained later. And if I take the power of 1 plus x to the alpha, then this is the equality here. And this is also sometimes important. So, so you might wonder, this alpha is a finite number, okay? So, and this series goes infinitely many degrees. So what happens when this power exceeds the number alpha? Then you just keep subtracting it until you get the negative infinity. So which means that this goes to alpha minus 1 to alpha minus n over n plus 1 factorial to the power of xn. Okay? Plus 1, sorry. Plus 1. So sine x and cosine x has a Taylor series at x equals to 0. These are also x, the c equals to 0. So center are all equal, c equals to 0. Okay, say c equals to 0, c equals to 0 of this form. And log function, the ln function has a c equals to the Taylor series as equals to 0 as this form. The difference between the cosine x and ln 1 plus x is that you don't have a factorial here. And also you have an alternating sign change. And also it starts from x, not 1. And also you can take the Taylor series of inverse of tangent as this form. Also there's no factorial. So these are the useful Taylor series. Useful in a way that you can manipulate many series using this Taylor series, and also these Taylor series are actually equals to the function itself. They're all equal. Okay. So it's also important to check the radius convergence of each sequence, each power series. So the first one, this one has radius 1, and this one has radius infinity, and this one has radius this one also has 1, and this one has infinity, and this one has infinity, and this one has 1, and this one also has 1. Okay. So let's try to use our Taylor series. Do I have time? Okay, so we have a few more time. So using the well-known Taylor series of known function, let's try to compute this. So this looks similar to this one, right? Tangent inverse. Okay. So if I plug x equals to 1, then what happens? It becomes the right-hand side of the power series exactly becomes this series, right? Now it's a question of whether this x equals to 1 sits inside of the interval of convergence. Does this Taylor series, does this power series converge at x equals to 1? And answer is yes, because when x equals to 1, it's an alternating series whose absolute value goes to 0, because absolute value is 1 over the odd number, and odd number goes to infinity. Therefore, it converges. It's okay to plug x equals to 1. When I plug x equals to 1 on the left-hand side, which is the original function, then it's a tangent inverse of 1, which is pi over 4. So we know that this goes to pi over 4. Okay? Using the Taylor series. How about this one? So it's an alternating series, but now the denominator becomes 1, 2, 3, 4. So it looks like I'm looking at this one, right? The Taylor series of log function, log 1 plus x, not log of x, okay? It's exactly the same when x equals to 1, right? X equals to 1, I get this series. So this must converge to ln 1 plus 1, which is ln 2, okay? And you also have to check whether this series, the power series, converge at x equals to 1. And the answer is yes, because it's also an alternating series whose absolute value goes to 0. How about this one? So you can use L'Hopital's rule in here easily. However, you can also use the Taylor series to find out the limit. So if you take the Taylor series of e to the x, it's 1 plus x plus 2 factorial x squared, and so on, and take minus 1 minus x and divide by x squared. So 1x are cancels out. What happens is on the numerator, the smallest degree of x is 2, and you're dividing x2. So we get this one is 1 over 2 factorial plus, now we had an x cubed over 3 factorial, but we divide by x squared, so we have x over 3 factorial, x squared over 4 factorial, and so on. So I'm taking limit when x goes to 0. So everything goes to 0 except for the first constant. So therefore it's 1 over 2. So without using L'Hopital's rule, you can easily find the limit using the Taylor series of well-known function. And also, let's look at this one. So we have on the denominator. So let's do this on the blackboard. So we have a here. Okay. ln 1 plus x squared on the numerator, but we didn't mention about such function in the Taylor series. However, it's the same thing when I replace x by x squared in the Taylor series of ln x plus 1. So here's the Taylor series of ln x1 plus x squared. So originally we had this x, but I replace x squared by x in the series. We have x squared square 2, x squared cube 3, and so on. So compare that with original definition of ln Taylor series of ln 1 plus x. I'm just taking x squared in the place of x. Okay. So that's the Taylor series of ln 1 plus x squared. You can safely use that. And how about 1 minus x cosine x? So 1 minus of x, so 1 minus x squared 2 factorial, x4, 4 factorial, and so on, right? That's the Taylor series. And 1 cancels out. We have x squared 2 factorial minus x4, 4 factorial, plus, and so on. Okay, so let's take the ratio. So when x goes to 0, what's the dominating term on this part? What's the dominating term on this power series? So x goes to 0 means that this higher power goes faster than the smaller power. So this is the dominating term. So this is equals to ln of x squared divided by, so in the denominator, this is the dominating term, x squared 2 factorial. So this is 2. Okay? Same thing for the sine x minus tangent x. Oh, did I mention the tangent x? Okay, so let's do the third one, the last one also. So we have a sine x as x minus x cubed 3 factorial and x fifth 5 factorial and so on. How do we take the Taylor series of tangent x? Since tangent x is sine x over cosine x, and sine x is x minus x cubed 3 factorial and so on, and cosine x is x minus x squared 2 factorial and so on, we can do the division of power series, as we did in the previous example here, to find out the tangent x, the power series of tangent x. So try to x minus x cubed 3 factorial, x fifth 5 factorial, and so on, divide by 1 minus x squared 2 factorial, x fourth 4 factorial, and so on. So we have x and x minus x cubed 2 factorial, x fifth 4 factorial, and then 1 over 2 minus 1 over 6. So actually, what I did in the previous example is this tangent, the power series of tangent. You see, in the previous example, previous slide here. So this is the sine x, this is the cosine x. I did tangent x. Okay, so this is the tangent x. Okay, so I don't have to do this again. So let's copy that. So this is x plus 1 over 3 x cubed plus 2 over 15 x fifths. Okay. And then what? Our problem is to find the limit of sine x minus tangent x divided by x cube. So then, so take this out, x minus x cube, 3 factorial, and so on, minus x plus x cube over 3, so on, divided by x cube. So x cancels out. So we have x cube. This is minus 1 over 3, minus 1 over 3, x cube, and so on. So there is a higher order term than 3. And if you divide by 3, this cancels out, and still the rest of the term contains x. So when x goes to 0, this goes to negative of 6, 4, 1, 3, 2, 3. So minus 1 over 2. Okay. You can also use the L'Hopital's rule because it goes to 0 on both denominator and numerator, but also you can use the Taylor series like this. Okay, let's try to finish this slide today. Okay, so the question is, so let me go back to the blackboard here. Okay, so we have a ratio of ln x plus x squared and then 1 minus cosine x. And x goes to 0. So we are comparing the asymptotic value of between this series and this series. When x goes to 0, x, the higher order power, goes faster than the smaller power. Okay? You can ignore that. So one thing that you might worry about is because even though this is very small, it might accumulate to a large number. But you don't have to worry about that because we know that this converges in the radius, in this radius is 1, it's also radius infinity. So the rest of the term is exactly look like x to the 4 times some finite number. A finite, not some, finite sum. Number, sorry. So although you have an infinite sum, this always converge. Okay? So and it converges to a finite number, and it applied with the x fourth. So you can rewrite if you want as x squared plus 1 plus some x squared times some number. So it's terms of px, but like this one. And we know that this px converges to finite number. So how about this part? So this is 2 factorial x squared 1 plus, and then x squared plus times q times x. And we know that this qx also converges because this cosine x has an infinite radius. So we know that qx converges to finite number. So when x goes to 0, we don't have to worry about the accumulation of the infinite sum in the tail here because it always converges to finite number. What only matters is the lowest order term in the sequence, in the series. And also has a x squared, so you can cancel out x squared, so that comparing the constant, you get this. Okay? Makes sense? So, okay, so we're almost done. Okay, so the theorem says if the radius convergence of power series given as R, then let's define a function f of x to be the value whose value is defined to be the limit of this power series. Okay. So I'm not starting from the function. I'm not talking about the Taylor series. I'm starting with the power series. Power series is a random number, an times some powers, okay? And I know that the radius convergence is R, so I can I can find a fixed number for this power series for x lying inside of this interval of convergence. So for those x inside of the interval of convergence, I can define a function whose value is exactly the limit of this power series. Then the theorem says this function is differentiable. Okay? Actually, it's infinitely differentiable, like C infinity, like before in the previous slide. And also the differential is defined to be the differential of each sum of differential of each sequence. Okay. So why this theorem is important? So proving this theorem requires uniform convergence and some more analytic statement. So just take that as a granted fact, and let's try to find out the evaluation of special types of sequence here. So I want to find the value, actual convergent value of the series in the first example. So when you're looking at this first one, n times 1 over 3 to the power of n, okay? It looks like, so n from 1 to infinity, okay? So it looks like someone had a differential on on each term and multiply 1 over 3 again. So when I rewrite this as 1 over 3 times n from 1 to infinity of n times 1 over 3 n minus 1, then it looks like it's 1 over 3 and ddx of x equals to 1 over 3. So let me write the sum first. So n equals to 1 to infinity of ddx at x equals to 1 over 3 to the power of n, right? So basically, the previous theorem says if I have a power series an x minus c to the power of n and take a derivative on x, then, so since I defined this to be f of x, this whole thing is f prime x. This is equal to the derivative of a sum of derivative of inside a function, inside of summation. So this is an times same as taking a derivative of each terms an x minus c to the power of n. So therefore it's an n x minus c to the power of n. So this is what theorem in the previous slide says. So it means that I can move my ddx to the outside of summation freely or make it into the inside of summation. So take this ddx outside of summation. We have 1 over 3 ddx x equals to 1 over 3 and 1 to infinity to xn. Okay? So what is this? So this function I can write as a well-known function because if I had one plus of these terms, this is a geometric series. So therefore, this ddx of x equals to 1 over 3, 1 over 1 minus x minus 1. Okay? Because I'm starting from n equals to 1, and this is not exactly the geometric series in the Taylor series, because geometric series in the Taylor series in the previous slide start from 1, okay, when n equals to 0. So I'm subtracting 1 in the result. So that's 1 over 3 times of 1 over x squared divided by minus 1, and x equals to 1 over 3. therefore it's 1 over 3 times minus 1, 1 minus 1 over 3 square. It's 1 over 3 minus 1, and it's 2 over 3, so 4 over 9. So it's minus, does it make sense? Minus, why do I take a minus here? How do I get the minus? I'm sorry, so it's a plus, sorry. I have to take a minus minus, so it's plus. It's plus. So it's so 3 over 2, okay? No, 3 over 4, sorry. 3 over 4. Okay? So it's quite interesting that we have a series, it looks like 1 over 3, 2 times 1 over square, 3 times 1 over 3 cube, and so on. It doesn't look like geometric series. It's not a geometric series, but also it's not, there's no consistent way of finding the value by simply looking at this series. Okay, I know that it will go up to some number, but I don't know what exactly that is. But using the Taylor series, our equivalent fact on Taylor series, you can exactly find the exact value of this series. And same thing for the others. There's a small hint that I can give you for the second equality, a second series, is that you have an n squared instead of n, right? Or n times n minus 1. So when you have n squared 1 over 3 to the power of n, then you can think about this as obtained by second derivative. So this is 1 over 3 d dx of n times xn, right? When x equals to 1 over 3, right? And then x equals to 1 over 3. And looking at this one, you have x times of n times x to the power of n minus 1, right? So you can take d dx, x equals to 1 over 3 of x times d dx of xn. Okay? So your sum n is obtained by taking a derivative twice. So if you take the summation, because of the theorem, I can move my d dx freely on outside and inside of the summation. So you can rewrite your rewrite your series as the derivative of some power series. So I will leave you this as on homework. Okay, so that's it for today. So we have a small thing to do further for the MATLAB, but today it's almost time, so we're going to leave that in the next week. So on the next week, we're going to actually solve the differential equation using power series. So thank you for listening, and if you have any question, please ask after class, and have a good lunch.